can self-supervised neural representations pre-trained on human speech distinguish animal colors? So for the introduction, so as you can probably guess, the topic is on bioacoustics. Bioacoustics is the study of animal vocalizations. Some people kind of look down on this sort of stuff. The last time I spoke to her, he wasn't particularly impressed by this topic, but now he's no longer the director, so all good. In recent years, the research has progressed in this thanks to all the approaches inherited from machine learning and deep learning. However, there are still some issues, specifically a lack of data, specifically labeled data. We also have less of domain knowledge in animal vocalizations or bioacoustics compared to human speech. And this is, to some degree, an understudied topic. However, in recent years, self-supervised learning has emerged as a way of leveraging lots of unlabeled data. So just to give a quick overview of the self-supervised learning framework, it typically involves 2 steps. First one is pre-training, where you have a large unlabeled corpus of data, and you would create, so you have unlabeled data, you don't have labels, but you create surrogate labels using a particular pretext task from the unlabeled data. And you thus optimize your learning objective, you do gradient descent. And the goal is to learn useful representations or representations which can be useful for a downstream task. So the second phase is called fine-tuning, where you would use these representations and fine-tune your model using the labeled data on a particular task, and this would supposedly give you better results than just a supervised training. The important part to remember in this is, in this pre-training phase, the network is just inferring the intrinsic structure of your input data, right? We do not at any point provide any explicit knowledge to the training. For example, we do not say anything about the speech production mechanism. The model is just learning the structure of the data. And to that end, we can say that the utility of these representations are not limited to just modeling speech. Because in speech and audio, you have speech as an acoustic domain, but you could also have music, you could also have biomedical signals, you could also have bioacoustic signals. Now I'll just give a small parenthesis on the different type of pretext tasks. So as you can imagine, the information that's encoded in these representations obviously vary a lot depending on the learning objective that one chooses, among other elements such as the architecture and so on. So at least in speech, the different type of pretext tasks can roughly be categorized into the 4 approaches given below. There are more than these, and the taxonomy keeps changing every few years. But in this work, we broadly categorize them into these 4 approaches. And this framework has yielded state-of-the-art results on a speech benchmark, which tabulates the different speech models based on their performance on different speech tasks. Now, coming back to bioacoustics, we can see that both humans and animals share a very simple commonality, which is that they both have a voice production mechanism. It might not be the same type of voice production mechanism, but they both have this system. And just as self-supervised learning models model the structure of human speech, which is inherently structured, the vocalizations produced by animals are also structured. And given this understanding and our understanding of self-supervised learning, the objective of this work is to investigate the cross-transferability of self-supervised learning representations learned and pre-trained on human speech for the purpose of analyzing animal vocalizations. There has been previous work which have explored this, for example, on tasks such as birdsong detection or bioacoustic event detection using contrastive learning. Some other people have looked into applying this to music and biomedical signals, but the generalization of these representations to animal vocalization has largely remained unexplored. So specifically, the research questions we investigate are the following. Number one, how discriminative are the embedding spaces of SSL models pre-trained on human speech? One. And two, can we systematically detect individual animal colors using said embedding spaces? And for this study, we focus uniquely on marmosets, which are these animals, just to narrow down our scope a bit. And these animals are quite widely studied in the NCCR evolving language. So a few words on the design of the study. First of all, the data set, we simply asked for this Marmoset data set, which was used and collected in a previous paper, and they just gave it to us for free, and it has very well annotated data. It contains audio vocalization segments of different Marmoset call types. There are 11 or 12 of them, called Twitter, fees, trills, and so on, as well as the identity of different Marmoset callers. So there are 12 different Marmoset identities who have different call types. And you can see the distribution given in the top graph. And the bottom graph, you have the log distribution of the vocalization lengths of different callers, in each color representing a different caller from 1 to 10. In total, we have something like 73,000 vocalization segments amounting to around 7.8 hours. And the data is imbalanced per color, as you can see in the above graph, but it's often like that in bioacoustics. Regarding the pre-trained embeddings models that we choose, we picked the following 11 models from the super benchmark, which I mentioned earlier. We have them pre-trained, or we take the pre-trained models, which were pre-trained on human speech on this corpus given below. We also give the number of parameters in millions and the dimension of the last layer embedding, which we will use for our classification purposes later on. And we also give the different pretext task or loss functions that these models were trained on, just so we can look at which objectives work better. So first, we try to do a color discrimination analysis. So we try to answer this first question about how discriminative these embedding spaces are. And we look at this from a interclass and intraclass variation framework. So in essence, we take all our raw audio vocalizations of variable length, and we send them through our pre-trained self-supervised learning models. And we obtain our extracted embedding. We specifically take the last layer. Then we take all the embeddings for the train set, and we sort them per color, so color identity. And then we split for each color all the embeddings into 100 different groups, just to effectively model the inter and intra-class distances. So these are the distribution of embeddings, which we model using a multivariate Gaussian distribution. So for each embedding, we calculate the mean vector and the diagonal covariance vector on each of these embedding spaces, and then we compute the intra-group distances and then the intergroup distances. The measures we use to calculate these distances between the two multivariate Gaussian distributions are KL divergence and Bhattacharya distances, which both have a closed form equation for a pair of Gaussian distributions. We can visualize our distribution of distances through a distance heat map. This is specifically for the wave LM model. So darker regions indicate a higher dissimilarity, and lighter regions indicate a high similarity. And we've aggregated all the distances in per color rather than per color group. So the diagonals represent the intra-color distances, and the off-diagonal represent the inter-color distances between groups. And in an ideal scenario, the intra-class distances would be smaller than the inter-class ones, just because the embeddings for a specific speaker would be closer together than across speaker, which is not entirely the case in our results. Nevertheless, for the callers where we have a large amount of data available, we do observe a good discrimination compared to callers which with a lower amount of data. So this analysis suggests that these embedding spaces do carry meaningful information for distinguishing Marmoset callers to a certain extent. However, accomplishing this with a simple linear classifier might still be a challenging task. Based on the insights of this study, we move on to our next caller detection study, which aims to answer the question of, can we systematically detect individual Marmoset callers using the set embedding spaces? And just as before, we had our extracted embeddings, and we calculated the mean and covariance vectors. We used them as concatenated functional vector of fixed length, which we then classify using a number of different classifiers for a caller detection task. So we have a vocalization segment and a claimed identity, and our classifier tells us whether these two are a match or not. So it's like a speaker verification, but in a simpler binary framework. And these are the classifiers we use, namely random forest, SVM. We use both the linear and non-linear version, AdaBoost. And we work in a 5-fold cross-validation framework. We tune hyperparameters for each fold, and we compute a grid search on the given search space below to find the optimal parameters. And the task, as mentioned earlier, is to do caller detection, and the metric we use for evaluating the performance is area under the curve. So this is the result of the different classifiers over 5 folds on the test set. We can see that on average, SVM, so nonlinear SVM, outperforms the other classifiers across all the embedding spaces, across all the pre-trained models. And the decision tree-based methods such as AdaBoost and random forest exhibit comparable performances for most of the models and consistently outperform linear SVM. So the SVM shown here is with RBF kernel, and the LSVM is the linear implementation. And this shows that the relationship between the features in the embedding space and their labels can be modeled by some methods to some degree, but not to the extent of nonlinear SVM. So that tells you something about the nonlinearity of these spaces. So before we look at the, here we're showing the detection performance per caller in distinguishing a positive class from the negative instances using SVM on a single test fold, whereas before we looked at all test folds across all models. And we can see that all callers are systematically distinguished in a binary framework, including the classes with a low amount of data. Next, we look at the average ROC curves of all models across all 5 folds. So the shaded area here is one standard deviation across all 5 folds, and the line is the macro average ROC curve. And we can see, so this is the SVM's classifier's performance across 5 folds, and we can see that all embedding spaces are capable of distinguishing Marmoset callers, which indicates that the models pre-trained on human speech can indeed generate salient representations capable of distinguishing animal vocalizations regardless of the pre-training criterion. And lastly, we visualize the relationship between the number of parameters and the detection performance for all the models. So the parameters against the area under the curve to see if there's any consistent pattern, and there isn't one really. The only interesting things we can see is that WaveLM's embedding space is more separable than the other mask prediction models given in red. But both the autoregressive reconstruction models given in blue perform as well as WaveLM with significantly fewer parameters, at least by one order of magnitude fewer. We also, so this suggests that all pre-training criteria yields competitive performance, but some may be more efficient than others, allowing smaller models to perform comparably to larger models. And lastly, but this is really specific, we can see that data to VEC, which is also mass prediction model, is much weaker than the other mass prediction models, despite being trained in similar conditions. But the points given here are more hypotheses than actual conclusions, because these require more analysis to be conclusive. So in summary, we investigated the applicability of such representations pre-trained on human speech to analyze animal vocalizations. We found that they can indeed classify vocalizations in the bioacoustics domain in a Marmoset collar framework. And these findings can be of great use to bioacoustic researchers looking to distinguish individual identities within a specific species in their acoustic data. Most of the work in the literature, they end up doing across species classification, but this is the first work we could find that actually did intraspecies classification, identity classification. Nonetheless, there are some limitations of this work, which I will present. For example, we only looked at embedding spaces of pre-trained model. We did not look at any traditional spectral features such as MFCCs. We also only use models pre-trained on human speech, but we could look at other models pre-trained on generic audio sets, like a general audio set, not necessarily just speech. We only evaluated our performance in a linear probing framework. We could also fine-tune our pre-trained model on a downstream task, which should improve results, but this is still ongoing. And we only looked at marmosets for this work, but we could look at other animals such as meerkats and so on. Thank you for listening. And if you have any questions, I'm all